This is B. Naresh, working as assistant professor in AC department. Today's topic is exact analysis of transistor amplifier using low frequency model. In this session, we are going to observe how the transistor acts as a amplifier, and for this amplifier, we are going to analyze parameters like the gain, input impedance, output admittance, and the gain in terms of current as well as the voltage by using the low frequency model or a small signal model. So let us consider, and we know that by using the transistor we can configure three types of the configurations. One is common base configuration, common emitter configuration, and common collector configuration. Based on all these three configurations depends upon the current gain, we identified that the common emitter configuration is the best configuration to design a amplifier. Hence, here I am going to use a common emitter configuration, and in this session, by using this common emitter configuration, and we know how it is acts as a transistor, means how it is acts as a amplifier. For this case, by using this common emitter configuration, and we know that here this terminal is a collector, base, and emitter, and based on the transistor construction, it contains the two types of the junctions. One is emitter base junction, another one is collector base junction. When the emitter base junction is a forward bias and a collector base junction is reverse bias, and then at this point the transistor acts as a active mode. At this active region, the transistor acts as a amplifier. For this case, to provide the faithful amplification, we also observed that the Q point analysis or operating point analysis, and always the Q point should be located in an active region, that is center of the DC load line. So once the transistor is a design for amplifier, we need to provide a constant collector current to stabilize the Q point in an active region to provide the faithful amplification. And from this active mode of configuration, let us consider, and the transistor type is NPN transistor. So means the collector is made with N-type material, base is made with a P-type material, and emitter is made with a N-type material. We need to satisfy this region, active region. Hence, we need to show that emitter base junction should be forward bias, collector base junction should be reverse bias. Let us consider the base is here acts as a input, collector acts as a output terminal. Base is made with a P-type material. Hence, this base material is biased with the positive pole of the DC source through a biasing resistance, that is base resistance. It is represented as RB. Hence, from this biasing, we can say that the input junction or a emitter base junction acts as a forward bias. Similarly, we need to bias the collector base junction should be reverse bias. Hence, the collector is made with N-type material. Hence, the collector is also biased with the positive pole of the battery through a biasing resistance, that is represented as RC. Hence, the collector base junction becomes reverse bias. And from this biasing, we can say that the transistor acts as an active mode of configuration. Hence, this transistor acts as a amplifier. Now we need to see this amplifier principle, and from this, let us consider, and for this amplifier circuit, in the absence of your given AC signal, means I considered as your input signal is a 0 means under the DC condition, we need to identify that how much base current is allows and how much collector current is flows across the amplified circuit. Hence, and if you want to observe the how much base current is flows in this network, then apply the KVL at input side means the input loop starts from VCC towards base resistance and towards the base terminal and base to your emitter and lower potential. If you apply the KVL at this input loop, means we need to identify that how much base current is the flows. Why? Because of that, in general, in a common emitter configuration, we know that the collector current is represented as beta times of IB plus 1 plus beta times of ICBO, where this ICBO is represented as reverse saturation current when the collector base junction is open circuited. If the reverse saturation current is much less than 1, IC is approximately equal to beta times of IB. Hence, with respect to this biasing, we need to observe how much base current is flows in this amplified circuit. Hence, we need to apply the KVL analysis at the input loop that starts from the VCC node to this lower potential through this biasing resistance and the base terminal and emitter terminal towards the ground potential. From this, if you want to write this equation, means the VCC is equal to the voltage drop across this base resistance is represented as IB times of RB. Along with, we know that the potential difference between this is the base terminal and this is the emitter terminal. The potential difference between base and emitter is represented as VBE. Hence, VCC is equal to IB times of RB plus VB. From this equation, we need to find out how much base current is the flows. So means we take this outside, hence it becomes VCC minus VBE by RB. And this is the base current flows in a network. And from this mathematical representation, where the VCC is the biasing source and the VBE is actually the potential difference between base and emitter terminal, and RB is acts as a base resistance. And if you observe this configuration, we made as a emitter base junction is forward bias. And we know that when the particular PN junction is a forward bias, the voltage drop across that particular PN junction diode is equal to cut-in voltage. Hence, from this representation, here the emitter base junction is also forward bias. Hence, the voltage drop across this forward bias junction that is equal to cut-in voltage V gamma. In general, the V gamma is either 0.7 volts or a 0.3 volts. If it is a silicon, that is 0.7. If it is a germanium material, that is 0.3. Hence, VBE value is much less than of the given DC biasing source. From this assumption, let if a VBE is much less than of VCC, so what happens here? IB is approximately equal to VCC by RB. So means that we are making this base current is a constant, where from this representation, VCC is the constant and base resistance is a constant. It makes that base current is also constant. By using this base current, now we need to observe from the generalized expression of common emitter configuration. We know that when the reverse saturation current is much less than 1, the collector current is represented as beta times of IB. This is under the DC biasing condition. Now let us consider when if the input signal is a passing through this network, and before going to that input signal, again we need to find out how much output voltage is flows here. To observe this output voltage means we need to find out the voltage drop between collector and emitter, that is represented as the potential difference between collector and emitter, that is VCE. If you want to observe this VCE, now you can apply the KVL at output side. So means we need to start from this VCC towards the collector resistance, towards the collector, and towards the emitter and the lower potential. So you can apply the KVL at output side. So we know that the starting source is a VCC, hence that VCC is equal to the voltage drop across this collector resistance is represented as IC times of RC plus the potential difference between collector and emitter is represented as VC. So from this equation, I represented as the VCE, that is equal to VCC minus IC times of RC. Now let us consider if the input signal is passing through this amplified network. Let us consider the given input signal is a sinusoidal signal, and let us assume that this is the VI. And during the positive portion of your given input signal, what happens here when the input signal is here I consider as the positive portion, means plus Vm. During the positive portion of the given input signal, and we know that the emitter base junction becomes forward bias. Due to that, the base current is increases. Why? Because of the maximum positive portion, the passing through this base terminal of NPN transistor, hence it increases the base current. If the base current is increases, so we know that from this representation, IC is approximately equal to beta times of IB. When the base current is increases, then automatically the collector current is also increases. Let us consider the output expression of this common emitter amplifier. Under this condition, now we need to find out the output voltage VCE. If you observe this, the mathematical relation of the output voltage, where VCC is the constant DC source minus IC times of RC. When during the positive portion of the given input signal, the base current is increases, hence it also increases the collector current. Hence, this drop, the voltage drop across the collector terminal is also increases. Why? Because of that, the collector current is increases, hence the voltage drop across the collector terminal is also increases. And here the VCC is made as a constant, while the base current is increases, the collector current is also increases, hence the voltage drop across this RC or collector resistance is also increases. Under this situation, it becomes more positive compared with this biasing source, hence VCE becomes a negative magnitude. From that representation, in this common emitter amplifier, the output voltage is 180 degrees with respect to your input signal. So from that analysis, here I drawn the response of the common emitter amplifier, and I considered as this is a input signal Vi. During the positive portion, what we observed here, the voltage drop across the collector resistance is increases. Hence, from this relation, VC is equal to VCC minus IC times of RC. Means if IC is increases, the voltage drop across the collector terminal is also increases. Hence, this this term is increases. Hence, the net total voltage becomes your negative magnitude. That is the reason. The output voltage is 180 degrees phase shift with respect to input signal. Hence, output voltage starts from the negative magnitude. During the negative portion, what happens? The voltage drop means base current is a decreases. Hence, the collector current is also decreases. If the collector current is a decreases, the voltage drop across the collector resistance also decreases. Hence, the total net voltage becomes positive. So, from this analysis, in a common emitter amplifier, the output voltage is 180 degrees phase shift with respect to input signal. So, now by using this amplifier analysis, we are going to represent the small signal model to observe the parameters like the current gain, voltage gain, input impedance, and output impedance. Before going to this small signal model, so already we discussed that the transistor is acts as a two-port network. So from this two-port network, we identified that so we have the four parameters like the input port, the parameters contains input current and input voltage. This is I1 and V1. At the port 2 or output port, again the two parameters are represented as I2 and V2. From these four parameters, we identified as two are the independent parameters and the two parameters are dependent parameters. If you want to represent a small signal model, the two dependent parameters are represented in terms of two independent parameters. From this transistor construction, we identified that the two dependent parameters are V1 and I2 means input by voltage. If you consider that common emitter configuration, that input voltage is represented across the base with respect to emitter, hence V1 is also represented as VB. And from that common emitter configuration, the output current is represented as collector current, that is I2 is nothing but the collector current. So there are two dependent parameters, input voltage and output current. These two dependent parameters are represented in terms of two independent parameters, that is base current and output voltage. So from this, we drawn that a small signal equivalent model from by using these two mathematical relations. If you observe this V1 is represented as HI times of means where we know that HI means input impedance, HR means reverse voltage gain, HF means forward current gain, and HO means output admittance. By using these two mathematicals, I represented, if you apply the KVL loop, then again it gives the same relation. V1 is equal to HI times of here, it allows the input current I1, hence HI times of I1 plus HR times of V2. Similarly, if you want to write this I2 expression, so if I2 is equal to HF times of I1 plus so H4 times of V2. Now we are going to analyze this by using this small signal model, the how this transistor acts as amplified and what are the parameters are affected in this case. So let us consider for this amplifier, and up to this point we know that this is the transistor is represented as a two-port network model, and this is a small signal model of BJT. For this small signal model for a BJT, Input side, I added the source resistance, that is Rs, along with the input voltage Vs. And output side, I'm going to measure the amplification across the load resistance. Hence, I added the load resistance, that is represented as ZL. And across this load resistance, it allows the load current, that is represented as IL. Now, by using this representation of the small signal model, this is the common. This is the two port or a small signal model of BJT. For this model, I added just the input side is the source resistance, and output side I added the load resistance. Across the load resistance, it allows the load current, that is represented as IL. Now, by using this model of or amplifier in a model of small signal, then we need to identify some important parameters, that is current gain, voltage gain, input impedance, and output admittance. So let us discuss the important parameters in this amplifier analysis. The first parameter is current gain or a current amplification factor, that is AI. So in general, we know that the gain means it is defined as it is a ratio of output parameter to the input parameter. In this case, we are going to observe in terms of the current. Hence, it is defined as it is a ratio of output current to the input current. That is, from this representation, from this statement of the current gain, and from this, by using this small signal model, the output current means output is measured across this load resistance. Hence, the output current is represented as IA. And from this small signal analysis, the input current is represented as I1. Hence, and from this definition of the current gain or a current amplification factor, this current gain is represented as AI, where A is the gain and the suffix this I indicates the parameter is related to current. Hence, the current gain is defined as it is a ratio of output current to the input current, that is IL to the I1. If you observe this again, the small signal analysis model, this is a collector current flows towards like this, and IL is a flows like this. Hence, the current flowing across the load resistance is opposite direction. Hence, this IL is also represented as minus I2. From this equivalent circuit, IL is represented as minus I2 and I1 is I1. Now from this, from the small signal model, we know that I2 is represented as HF times of I1 plus H4 times of V2. Again, from this, here I am going to represent then V2. So parallelly, voltage is the same. Hence, this V2 is absorbed across this load resistance. V is nothing but a in terms of the product of current and resistance. Hence, to if you want to observe the how much voltage is a flows across this load resistance, that is represented as in terms of current and resistance. Across this load resistance, we observe that the load current is a flows, that is represented as IL times of your resistance is ZL. And we know that from this configuration, the load current is also represented as the collector current, but the flow of direction is opposite. Hence, it is represented as minus I2 times of ZL. Now I am going to substitute this V2 in this expression to observe how much output current is flows with respect to this small signal analysis. Now we know that this I2 is HF times of I1 plus H4 times of V2. So hence this V2 is replaced with this value. So what is the V2 value? Minus I2 times of ZL. Now we can simplify this one. So to observe the I2 current or to observe the gain parameter, just so if you expand this term, what happens here? I2 is equal to HF times of I1, and this is plus into minus means minus HO times of I2 into ZL. Take this I2 terms outside. Now it becomes I2 plus this is minus term, hence it is a plus HO times of I2 into ZL, that is equal to this HF into I1. So from this, and if you take the I2 is a common term, now what happens? So from this, I'm going to find out this I1. If I1 is equal to I2 plus HO times of I2 into ZL by HF. Now again, this I1 is equal to, in this case, take the I2 is a common term. So I2 is a common term, means 1 plus HO times of ZL by HF. So this is I1 representation in terms of this small signal parameters here. And we know that the current gain is represented as it is a ratio of output current to the input current. So hence from this we derive that it is a ratio of minus I2 to the I1. So now can substitute this I1 value here to observe how much current gain is generates here. So for this case, this is minus I2 is a minus I2 divided by, now we can substitute this I1 value. What is the I1 value? I2 times of 1 plus HO times of ZL by HF. Now we can simplify this one. I2 is a get cancel, HF is a outside. So means minus HF by 1 plus HO times of ZL. So this is current gain in terms of small signal analysis parameter or a low frequency model parameters here, where the HF is represented as forward current gain. That is also we can write the beta. Beta is also represented as HFE. So why I'm writing here HFE means this is observed with respect to the common emitter configuration. Hence HFI is replaced with HFE. So in this common emitter configuration, if you want to write this current gain, so means that is minus HFE by 1 plus HOE times of ZL. So this is a factor for if you are using the common emitter configuration. Now we are going to identify another parameter, how much input impedance is offered by using a low frequency model. Hence, so we know that generally the input impedance is represented as, so in this case I neglected the source resistance. I'm going to calculate in terms of across this port 1 how much input impedance is offered with respect to this one input port 1 and 1 dash. And from this, we know that input impedance is defined as it is represented as input voltage to the input current. From that, we can say that the ZY, the ZI indication that input impedance, it is a ratio of input voltage to the input current. Means input voltage is, I consider this is the small signal model. So at this point, the input voltage is V1. And input current means across this small signal model, the input current is represented as I1. Now we need to find out V1 and I1 parameters here. And from the small signal model or a low frequency model, we know that V1 is equal to HI times of I1 plus HR times of V2. So in this expression, I'm going to substitute this V1 here in input impedance. It is a ratio of input voltage to the input current. So hence, and from the small signal model or a low frequency model, so or a H model, the V1 is represented as HI times of I1 plus HR times of V2. Hence, I'm going to substitute this V1 with here. Then, so what happens here? So if I1 is a get cancel, means in this term, this is the HI plus HR times of V2 by I1. Now again, already we discussed that V2 is represented as IL times of ZL. So from that, we define that this AI is represented as it is a ratio of output current to the input current, that is IL times IL by I1. So from this, how to write this IL here? IL is equal to AI times of I1. Means the input impedance I am going to represent in terms of gain parameter. Hence, this IL is replaced with this parameter here. So what is the IL? IL you can also write AA times of I1. Hence, AA times of I1 and this ZL is the ZL. Now we can substitute this V2 here. So what we observe here, ZI is represented as HI plus HR times of V2 by I1. So what we observe the V2 here. So V2 is represented as AI times of I1 into ZL. So hence the same parameter represented in the V2. This V2 is replaced with this term AI into I1 into ZL by I1. So hence I1 is a get cancel. So what happens? This is HI plus HR times of AI into ZL. So this I1 is a get cancel. So this parameter is equal to HI is HI plus HR AI into Z. And again, from this, we observe that the current gain is represented as minus HF divided by 1 plus HO times of ZL. You can use this formula, or otherwise you can substitute this current gain in this representation. So now the input impedance becomes HI plus, and AI contains minus HF by 1 plus HO times of ZL, hence minus HR into, so this AA is replaced with HF by 1 plus HO times of ZL into ZL. Means again, the ZL is a get cancel. Now it becomes HI minus HR HF. So that is 1 by ZL plus H naught. So means that becomes HI minus HR HF by 1 by ZL plus H. So that is equal to input impedance in terms of small signal model parameters. Similarly, we need to observe how much voltage gain or amplification factor is generated. And again, we know that the gain means it is a ratio of output voltage to the input voltage. At this point, the output voltage is V2 and the input voltage is V1. Hence, from that, the voltage gain is derived and defined as it is a ratio of output voltage to the input voltage. So we observe that V2 from this network. What is the V2? V2 is equal to IL times of ZL. From, if you observe this network, the V2 is observed across this node, means the parallel with this impedance, load impedance. So V2 is equal to IL times of ZL. And again, we know that if you want to represent in terms of the gain parameter, so we know that AA is represented as it is a ratio of output current to the input current, IL by I. From this relation, the load current IL is represented as AA times of I. Hence, the V2 becomes IL is replaced with AA times of I1 into ZL. So hence, the V2 I represented as AA times I1 times of ZL by V1. So from this case, so what happens here? So that is represented as V2 by V1 is equal to. So if you observe this one, this product I1 by V1. So we know that the input impedance ZI is defined as it is a ratio of input voltage, or means it is a ratio of input voltage to the input current, means V1 by I1. So this is nothing but the reciprocal of the impedance, hence I represented as 1 by ZI. So this is the voltage gain is observed by using the a small signal model or a low frequency model for this amplifier. Now another parameter is output admittance. That admittance is represented as Y0. So if you observe this one, And for to observe this one, we need to make this input voltage is a zero, and this input means output load resistance or a load resistance we observe as infinite. From that, it is defined as it is a ratio of output current to the input current. Hence, the output admittance is represented as I2 by V2. From this, again, we know that from the small signal model, the I2 is represented as HF times of I1 plus H4 times of V2. Now we can substitute this I2 here, so that Y0 is equal to I2 by V2, that is equal to HF times of I1 plus H4 times of V2 by V2. Now you can simplify this analysis. So what happens? HF times of I1 by V2 plus this V2 is a get cancel here for this term. Then it becomes H4. And here I'm going to observe with respect to this when the input voltage is a 0. From this, I'm going to apply the KVL at input circuit when the Vs is equal to 0. So means that Vs is a 0 means this voltage source is replaced with a short circuit. So the source is replaced with a short circuit. Hence, we assume that Vs is a 0. When the Vs is a 0, then the voltage drop across this Rs is represented as Rs plus I1. And the voltage drop across this input impedance that is represented as HI times of I1 plus HR times of V2 that is equal to 0. From this, I'm going to observe the I1. So what is I1 here? So if you take I1 is a common term, this is Rs plus HI that is equal to minus HR times of V2. From that, the output admittance. So if I1 by V2, then so it becomes minus HR by Rs plus HI. And we know that output admittance is represented as it is a ratio of output current to the output voltage. So from this, you can define this is minus HF into HR by Rs plus HI plus H4 term. Now I'm going to consider the voltage gain along with this source resistance. In the previous case, we are not considered the source resistance. Now here I'm going to consider the voltage gain including the source resistance that is Rs. From that, it is represented as AVS means the voltage gain including the source resistance. Now it is defined as it is the ratio of output voltage to the input voltage. In a previous case, we considered as V2 to the V1 means input voltage we consider only the V1 means across the port 1. Now we are going to consider with respect to the source resistance that is Rs. So hence the input voltage is Vs. Hence V2 by Vs. We can also write this term in terms of V2 by V1 times of V1 by Vs. Again V1 is a get cancel, that is equal to V2 by Vs. So means this network is a simplified here. So entire. So this is Rs and this is the voltage source. This entire part is represented as your input impedance that is Zi, and across this Zi we represented as your V1. Hence, so we know this V2 by V1 is nothing but a voltage gain AV times of V1 by V means we are going to consider this voltage gain including with respect to source resistance. Now we need to find out how much voltage drop is generated with respect to this source. So to calculate this, V1 is equal to means let us take some current is flowing. So means I times of Zi. And from this loop again, what is I? I means V by R. V means that is your voltage source Vs, and total resistance means Rs plus Zi. Hence from this, the voltage drop across this 1 and 1 dash that is represented as Vs times Vs by Rs plus Zi into Zi. So that is the reason. Here I represented as the V1 is equal to the same relation. So Vs into Zi by Rs plus Zi. Now we can substitute this here. V1 from this we can observe. So the Vs is taken this outside, it becomes V1 by Vs. So from this, the V1 by Vs becomes Zi by Rs plus Zi. So hence I substituted this here in a voltage gain. Similarly, so this is we observed already the voltage gain AV is represented as AA times of ZL by Zi. Now you can substitute this parameter also here. Now this AV is replaced with AA times of ZL by Zi. So now it becomes AA times of ZL by Rs plus Zi. And this Zi is a get cancel here when you substituting this one. AV means AA times of ZL by Zi into Zi by Rs plus Zi. So this Zi is a get cancel. Hence, the AVS is represented as AA times of ZL by Rs plus Zi. Similarly, we need to identify the current gain including the source resistance, that is Rs. So means now we need to convert this. We have the voltage source input side. This voltage source is converted into current source according to your Norton's theorem. So then it is replaced with voltage source is replaced with the current source. When we are converting this voltage source with the input current source, the resistance is in parallel with the current. So hence this is Is and Rs, and the input side this is the total input impedance. So here we need to find out how much voltage. From that current gain representation, again it is defined as it is a ratio of output current to the input current. Means, or we can write this is IL by Is. We know that IL is there is minus I2 by Is. That should be represented in terms of current gain minus I2 by I1 times of I1 by I. So this minus I2 by I1 is also represented as AI times of I1 by Is. Hence, so now I'm going to substitute what is how much I1 is a flows here from the circuit. So the I1 means is represented as Is times of Rs by, so the total resistance is Rs plus here Zi. Now I can substitute this I1 here in this case. So that is I1 is represented as, so this is A1 times of I1 means Is into Rs by Is into Rs plus Zi. So this Is is a get cancel. Then it becomes AA times of Rs by Rs plus Zi. So this is the parameter with respect to your source resistance. So up to this point, today we observed how the transistor is acts as amplifier, and we also identified that some important parameters by using the low frequency model. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.